All right, let's take a look at this. The official title is Sheer Exfoliated Pristine Graphene Casein Zinc Oxide GC3N4 Quaternary Biocomposite. Whew, I know, that is an absolute mouthful. But what if all of that complicated science boils down to one single incredible question?
What if we could build skyscrapers out of milk? I know, it sounds completely nuts, right? Like something out of a sci-fi movie. But it actually points to a very real solution for a massive global problem we're all facing. You see, our entire world is basically built on concrete. After water, it's the most used substance on the planet. But here's the catch. Making all that concrete is a huge driver of climate change. We're talking nearly 10% of all global CO2 emissions. That's a staggering number.
So, we need another option. And according to this new research, we might just have one. Scientists have created a high-performance, bio-based material that could literally change everything about how we build our world.
So what's the secret sauce? Well, it's kind of like a super recipe with 4 key ingredients. Let's meet the team of molecular superheroes that make it all possible.
First up, we've got casein. This is the main protein you find in milk. In this recipe, it's the matrix. Think of it as the bio-friendly, super abundant glue that holds the whole thing together. It's our foundation.
Next, you've got to add the muscle, and that's graphene. Now, this stuff is just incredible. It's a sheet of carbon that is only one single atom thick, and it happens to be the strongest material we have ever tested. Its job here is to provide unbelievable strength. Then we bring in the shield, zinc oxide, or ZNO. This little nanoparticle is like a triple-threat bodyguard. It adds extra strength, sure, but it also blocks 95% of harmful UV radiation, and it's powerfully antimicrobial. It kills over 99.99% of bacteria it touches. And our final ingredient is the matchmaker, graphitic carbon nitride, or GC3N4. This is the clever molecule that makes the whole team work. It helps all the other parts play nicely together, adds fire resistance, and even gives the material self-cleaning powers. So how do you combine them? First, you mix the ingredients. Then you use a process called shear exfoliation. Think of a ridiculously powerful kitchen blender that peels apart graphite into those amazing graphene sheets right inside the mix. After that, the molecules are chemically linked together to form a stable gel, and finally, it's all squeezed and heated into a solid panel. It's a surprisingly elegant process.
Okay, so that's the recipe. But what happens when you actually put it all together? Well, you get a material that is stronger, lighter, and a whole lot smarter than what we have today. Just take a look at this chart. This is the metric that really matters, specific compressive strength. It's basically the strength-to-weight ratio. And as you can see, this new material compared to timber and concrete, it's not even a fair fight. It's in a whole different league.
In fact, let's put a hard number on that. Pound for pound, this new material is 23.7 times stronger than concrete. Let that sink in. Nearly 24 times stronger. That's not just an improvement, that's a complete game changer.
And remember, raw strength is just the beginning. This stuff has a whole list of built-in superpowers. It blocks UV, kills germs, cleans itself, resists fire and moisture. And get this, it's electrically conductive. That means it can actually sense stress and damage in itself.
So this is all amazing in a lab. But what does it mean for the real world? How could this stuff actually revolutionize the way we build, right now?
Well, think about a normal wall in a building. It's made of multiple, heavy, passive layers. Drywall, insulation, vapor barriers, siding. With this composite, you could replace all of that with a single lightweight panel that does everything. It's the structure, the insulation, and a smart sensor all rolled into one.
And remember that matchmaker molecule? It gives the material photocatalytic properties. That means we could build facades that literally clean the air, that use sunlight to break down smog and pollution, essentially turning our skyscrapers into giant self-cleaning air purifiers. And because it conducts electricity, the material itself becomes a sensor. This leads to an incredible concept, infrastructure that can tell us when it needs repairs. It could detect tiny cracks in a bridge or strain in a beam long before a human inspector ever could.
But honestly, all of that is just scratching the surface. This isn't just a new material, it's a platform for the future. And the possibilities get even more mind-bending.
Take aerospace, for example. You could build lighter, stronger skins for drones and airplanes that are naturally resistant to corrosion and the intense UV radiation you get at high altitudes, all while being more sustainable.
Or how about we think bigger, like off-planet big? We could potentially use materials found on the Moon or Mars, mix them with a binder like this, and 3D print entire habitats that also shield astronauts from dangerous cosmic radiation.
And here's where it gets really wild. You could engineer the material to act as a structural supercapacitor. This means your walls and floors wouldn't just hold the building up. They could store and release electricity, acting as a giant integrated battery for the entire structure.
Okay, let's bring it back down to Earth for a second. This all sounds fantastic, but when can we actually start building these futuristic milk-based cities? We have to be realistic about the hurdles that are still ahead.
You know, there are still some pretty big questions we need to answer. Scientists have to prove it can last for 50 years or more out in the real world. They need to figure out how to go from making small sheets in a lab to mass-producing giant panels in a factory. And of course, you have to get it approved by building codes and develop the software to design with it.
But even with those challenges, the potential is just undeniable. We're talking about going from a simple byproduct of the dairy industry all the way to building self-healing bridges and deep space habitats. It really feels like this material could build the world of tomorrow. The only question is, what will we build with it first?